We start the course quantum mechanics. The first unit is particle properties of waves, and the first topic is blackbody radiations. Let us first familiarize ourselves with electromagnetic spectrum. Now here I have arranged different regions of electromagnetic spectrum in the decreasing order of wavelength or increasing order of frequency towards right. Okay. So there are mainly 7 regions. These are not these are bands. We have to understand these regions as bands. That means each region has a frequency band or wavelength band. It's not that a particular radiation has a single wavelength. Okay, so let us start with the longest wavelength region, radio waves. The wavelength typical of radio waves, wavelength range typical of radio waves is 100 kilometer to 10 centimeter. So they are very huge waves. Wavelength can be up to 100 kilometer. It can be as small as 10 centimeter. Here I have converted these common units into meters, standard unit. Okay. So next lower wavelength will be microwaves. So in each region, let us keep in mind that we should keep in mind if we are normally the common practice is to talk in terms of wavelength. So we should keep in mind a characteristic wavelength of each region. So for radio waves, we can say it's of the order of kilometer, okay, or a few meters. Mainly we can say up to 100 meters to 1 kilometer. That is the range. Okay, so that is a typical order. So the range can be greater than 1 kilometer, can be less than 100 meter, we know, but this is the a few meter, we know, but this is the typical range, typical characteristic wavelength of radio wave region. So similarly for microwaves, okay, the range is from 1 centimeter to 1 millimeter. So we can keep in mind that the typical or characteristic wavelength of microwave region is in millimeters. Okay, it can be 1 millimeter, it can be slightly less than 1 millimeter, okay, or a few millimeters. So a few millimeters is so it's of the order of millimeters. That's what we can keep in mind. Okay, so again I have converted this into meter. 1 millimeter is 10 raised to minus 3 meter, as you know. The next lower wavelength is infrared region. Okay, infrared region is named because its wavelength is greater than red. Okay, red will come in the visible region. So infrared region, the range is from 0.1 millimeter to 1 micrometer. Micrometer means 10 raised to minus 6 meter. Okay, I have again converted into meter here. So what is the typical wavelength region in infrared? A few micrometers. Okay, so keep in mind that a few micrometers. Next lower wavelength is visible light, to which our eyes are sensitive, to which the eyes of all the living organisms on the earth are sensitive. Now in visible region, the longest wavelength color is red, the shortest wavelength color is violet. In between there are other colors. The range is 700 to 400 nanometer. Red has a wavelength of 700 nanometer, of the order of 700 nanometer. Violet of the order around 400 nanometer. Nanometer means 10 raised to minus 9 meter. 1 nanometer is 10 raised to minus 9 meter. Usually a characteristic wavelength of visible region is represented by green light, which is around 500 nanometer. Okay. If you convert this, so what is the characteristic region of characteristic wavelength of visible region? We can say around 500 nanometer. Okay, so if you convert into meter, this 700 into 10 raised to minus 9 nanometer is 10 raised to minus 9. So we have 7 into 10 raised to minus 7 meter. Here 400 nanometer is 4 into 10 raised to minus 7 meter. Okay, this is visible region. The next lower wavelength is ultraviolet. It is named because this region has a wavelength shorter than violet. Okay, so it ranges from 400 to 10 nanometer, ultraviolet region. So we can keep in mind that the typical wavelength of ultraviolet region is 10 nanometer, a few tenths of nanometer. Okay, again I have converted this into meter. The next lower wavelength region is X-ray, 1 nanometer to 10 picometer. Picometer means 10 raised to minus 12 meter. 1 picometer is 10 raised to minus 12 meter. So this is 10 raised to minus 9 to 10 raised to minus 11 meter. Right? When nanometer is 10 raised to minus 11 meter, picometer is 10 raised to minus 12 meter. So 10 picometer is 10 raised to minus 11 meter. So the average of this is 10 raised to minus 10 meter, which we call angstrom. 10 raised to minus 10 meter is 1 angstrom, named after the experimental physicist Angstrom, who made fundamental contributions in spectroscopy in the middle of 19th century. Remember that in the previous class, in the introduction, I have mentioned that in hydrogen spectral series, in the visible region of hydrogen spectral series, which we call Balmer series, the most prominent line, most intense line is a red line, which we call or name H-alpha line. This was first discovered by Angstrom in 1853. So his name we use for very short length. So 10 raised to minus 10 meter is called 1 angstrom. So my point is that in X-ray, the typical wavelength we can keep in mind that of the order of 1 angstrom. It's greater than 1 angstrom. It can go up to 10 angstrom, that means 1 nanometer. It can go up to 10 raised to minus 2 angstrom. No, 10 raised to minus 1 angstrom. That is 10 raised to minus 11 meter, okay, or 10 picometer. So typically it is of the order of 1 angstrom, X-ray region. Then the still lower wavelength region is gamma ray region. The wavelength starts of the order of 1 picometer, which is 10 raised to minus 12 meter, and it can go up to very low values. Whatever be the lower wavelength beyond this, we call simply low wavelength gamma rays or high frequency gamma rays. So there is no other separate region after this. So these are the 7 major regions of electromagnetic spectrum, and you should study this order. You should keep in mind this picture, the way these different regions are arranged this is more convenient in the decreasing order of wavelength. So you can start with the maximum wavelength to continuously to different wavelengths, and keep in mind always the typical wavelength in each region. This will be useful for later calculations, etc. And suppose in some situation we want to know the frequency of each region of the electromagnetic spectrum. We know the relationship is that frequency into wavelength is equal to speed of light. And what is speed of electromagnetic radiation or speed of light? Usually we use light to represent any electromagnetic radiation. It is the symbol used is C, which is approximately 3 into 10 raised to 8 meter per second in vacuum, right? So frequency is C by lambda, but if we want only the order of frequency, instead of C we can take of the order of 10 raised to 8. Okay, so if you substitute here the order of wavelength, you can get the order of frequency. Okay, I have done here 2 typical examples. One is radio waves. If you do this calculation, that means take C as of the order of 10 raised to 8. Take these values, let us say 100 kilogram. What is 100 kilogram? 100 into 10 raised to 3. That is 10 raised to 5 meter. So 10 raised to 8 by 10 raised to 5 is 10 raised to 3 hertz. That much hertz. Again, we know hertz was Henrik Hertz, who discovered, who first produced transmitted and detected electromagnetic radiations, radio waves. He first produced. So the first experimental evidence of electromagnetic radiations came from Hertz, Henrik Hertz. He was also the person who discovered photoelectric effect. That was in 1887. So frequency is named after Hertz. So this 10 raised to 3 Hertz means kilohertz. And on the other extreme, 10 centimeter means 10 raised to minus 1 meter. So 10 raised to 8 by 10 raised to minus 1 will be 10 raised to 9 Hertz, which we call gigahertz. So the typical frequency range of radio waves is from kilohertz to gigahertz. In between there can be 10 raised to 6 Hertz also, megahertz. So kilohertz, megahertz, gigahertz, etc. or frequency ranges of radio waves. And let us look at our visible light. At least these two regions you can remember. Visible light, the typical wavelength we know it is 500 nanometer, which is 5 into 10 raised to minus 7. So let us say 10 raised to 8 divided by 5 into 10 raised to minus 7. Okay, so let us substitute, let us say 3 into 10 raised to 8 by 5 into 10 raised to minus 7. 3 by 5 is 0.6, and 10 raised to 8 by 10 raised to minus 7 we get 10 raised to 15. So 0.6 into 10 raised to 15 is 6 into 10 raised to 14. So we can say it is of the order of 10 raised to 14 hertz. So that, keep that in mind. Along with radio waves, you can remember visible light, the frequency, typical frequency is 10 raised to 14 hertz. Okay. In the same way, in all other regions, if you want at any stage what is the typical frequency, okay, just you divide 10 raised to 8, take the order of c, speed of light in vacuum, 10 raised to 8 divided by, substitute the typical wavelength, okay, in each region. So you will get the frequency of each region. There is no need to remember the frequency, anytime you can do the calculation. So but this picture of electromagnetic spectrum in terms of wavelength you should keep in mind. It should be handy. It will come handy in many situations when we do many calculations. Okay. We need to know, in addition to the wavelength of each region of electromagnetic spectrum, we need to know what is the energy of one quantum of radiation. That is energy of one photon in different regions of the spectrum. So what is the equation for the energy of a photon? E equals h nu, where nu is the frequency of the radiation and h is Planck's constant. Okay, this was first wrote down by Einstein. Okay, so this we will discuss when we discuss in detail when we consider photoelectric effect. Okay, so this is the energy of one photon. If you want to express this energy in terms of wavelength, we know frequency is c by lambda, so we have hc by lambda. Okay. Now h is Planck's constant. The most accurate value according to the present measurements is this 6.62607015 into 10 raised to minus 34 joules second. Look at the order of the value, 10 raised to minus 34. It is very small. Look at the units, joules second. That means the dimension is energy into time. Okay. Usually when we do calculations, we will use this up to 3 decimal points, 6.626 into 10 raised to minus 34 joules second. Speed of light in vacuum, the symbol is c, which is approximately 3 into 10 raised to 8 meter per second, but the most accurate value is 2.99792,458 into 10 raised to 8 meter per second. Okay. When we do more accurate calculations, we have to use this value c up to 3 decimal points, 2.998. Okay, this is fourth decimal point is 9, so we can approximate this as 2.998 into 10 raised to 8 meter per second. Okay, now look at this one, this expression. Most of the time, I have stated this during the previous slide. That is, when a spectral line or a radiation is given, most of the time instead of frequency, its wavelength will be given. Most of the time. So the question is, once wavelength is given, how do we calculate the energy of a photon? So from this expression, it is clear that hc has the dimension of energy into length. Okay, because left hand side you have energy, denominator you have length, so hc should have the dimension of energy into length. Length will cancel and you will get energy on the right hand side. Or look at these two units. H has the dimension unit joules second, c has the unit meter per second. If you multiply, hc will have joule meter. So hc, the SI unit of hc is joule meter. But we always want to know the energy of photons in terms of electron volt. Why? Because electron volt is a very small unit of energy. Photons usually have very small energy. So instead of saying that 10 raised to minus 8 or 10 raised to minus 14, okay, like very small 10 raised to minus 19. So always instead of carrying this very low powers of 10 around, if we use joule, it's better to use a very small unit of energy. Just like when we talk about wavelength of spectral lines, for example, wavelength of radiations, for example, X-ray. We know that the typical wavelength of X-ray is of the order of 10 raised to minus 10 meters. So instead of always speaking 10 raised to minus 10 meter, it is better to use a single unit for that small length, which is angstrom. Okay. So that is so always. So when we have to use a very small unit, let us define a small unit. Okay, when we have a very small quantity of energy, let us define a small unit of energy. Okay, this is electron volt. So we want to convert this Hc from joule meter. So it has the unit joule meter. Let us express in electron volt meter. That is, I want to convert joule into electron volt. How do we define electron volt? 1 electron volt is defined as, we know that when a charged particle is accelerated through a potential difference, its kinetic energy increases. Okay, for example, you have a positively charged particle, you put a negative plate here. If it is starting from rest, it is accelerated through the negative plate, then it gains some kinetic energy. Similarly, if there is a positive plate, it's already accelerating, then it can be decelerated also. Okay, so consider a single electron, one electron accelerated through 1 volt potential difference. Okay, you have an electron, let us say at rest, you have a positive terminal here, then this electron will be accelerated to the positive terminal. So from rest it is accelerated, so when it reaches here, it has gained some kinetic energy. So what is the kinetic energy gained by a charged particle when it is accelerated through a potential difference of V volts? Suppose the charge of the particle is Q. So this gain in kinetic energy is Q into V, charge into potential difference, right? So if 1 electron is accelerated through 1 volt potential difference, what is the gain in kinetic energy? Its charge Q. What is it? E, electronic charge, 1.602 into 10 raised to minus 19 coulomb. Q into V. What is V here? Potential difference, 1 volt. Okay, so the kinetic energy gained is 1.602 into 10 raised to minus 19 into 1. That is 1.602 into 10 raised to minus 19 joules, which is a very small quantity, 10 raised to minus 19. This small unit of energy, 1.602 into 10 raised to minus 19 joules, is defined as 1 electron volt. Okay, so we have this relation here, 1 electron volt equals 1.602 into 10 raised to minus 19 joule. The kinetic energy gained by a single electron accelerated through a potential difference of 1 volt. Okay, so then we can see that if we have, let us say, x electron volt, how do we convert that into joule? You just multiply with the electronic charge, 1.602 into 10 raised to minus 19, x into 1.602 into 10 raised to minus 19 joule. Suppose we have energy in joule, how do we convert into electron volt? Take this electronic charge to the left side. We have 1 joule equals 1 by 1.602 into 10 raised to minus 19 electron volt. So to convert energy from joule to electron volt, you divide with the electronic charge. To convert from electron volt to joule, you multiply with the electronic charge. Okay. Here we have Hc. Hc is in joule meter. We want to express this in electron volt meter. So we have to divide with electronic charge. Let us do this calculation. So Hc, the value of H is up to 3 decimal points, 6.626 into 10 raised to minus 34 joule second. And the value of C up to 3 decimal points is 2.998 into 10 raised to 8 meter per second. Second will cancel. We have joule meter. Now we want to convert it into electron volt meter. We divide with electronic charge. Now we have electron volt meter. You do this calculation. I have written the result here, but you should substitute and do this calculation. You get this one, 12.39997 into 10 raised to minus 7. Okay, let us rewrite this. I am taking 2 decimal points to the right side. Okay, then you will have an additional 10 raised to minus 2. Then this will become 10 raised to minus 9. This is for convenience of writing. Okay, so what do you have? 1239 or 1239.997. Right? This 0.997 is approximately 1. Right? Or I can take this 0.997 as 1 and add this 1 to 1239. So it will become 1240. Right? 1240 or 1240 into 10 raised to minus 9 electron volt meter. This is for convenience of remembering. And also another thing is that this 10 raised to minus 9 I can combine with this meter. We know 10 raised to minus 9 meter is nanometer. So I can write HC is 1240 electron volt nanometer. It's a nice whole number. You can remember it easily. 1 plus 1 is 2, 2 plus 2 is 4. Like that you can remember, or you can use any other mnemonic technique. Whatever you use, it's better to remember this number. So my suggestion is this: you should do this calculation once and for all in your life, and after doing these calculations and after getting this value and after approximating to this, always remember this value 1240 electron volt nanometer, because you will always encounter in modern physics, in the study of modern physics, in almost everywhere, wherever you turn, wherever you want to do some numerical calculations, most of the time you will encounter this combination HC. Okay, so this value will come in handy always. There is no need to substitute H, C, then convert into electron volt by dividing with the electronic charge. Okay, you do this once and for all and then remember this value. Okay, so 1240 electron volt nanometer I have written here for calculations in atomic physics. The reason is that in atomic physics, we are all, most of the time we are dealing with energy in electron volts, a few electron volts, because in atomic physics we are interested in transitions of electrons between valence orbitals. Okay, valence orbitals, that means outermost orbits. So the energy difference between outermost orbits in an atom is of the order of a few electron volts. So when we know that when an electron, this is I'm anticipating Bohr atom model here, but you have studied it in your higher secondary classes. So in Bohr atom model we know that when an electron de-excites from a high energy state to low energy state, that difference in energy will be emitted, or if it excites from a low energy state to high energy state, that much energy will be absorbed. Okay. Since the energy difference between valence electronic states is a few electron volt, during the electronic transitions the amount of energy absorbed or emitted is of the order of a few electron volts. Okay, so we are interested in that's why I'm saying that we will deal with a few electron volt energy in most of the time in atomic physics. There are other situations like transitions between inner electronic states closer to the nucleus. That energy difference is of the order of kilo electron volt. Okay, that is okay. That is also there. But most of the time we will be dealing with electron volt energy. So this value we will always use in terms of electron volt nanometer for calculations in atomic physics. When you come to nuclear physics, the situation is different, and a typical energy difference between nuclear energy level is of the order of mega electron volt. So when there is a transition between nuclear energy levels, the amount of energy absorbed or emitted will be mega electron volt. So it is better to rewrite this value in terms of mega electron volt when we do calculations in nuclear physics and also in particle physics. How do we convert this into mega electron volt? In order to convert electron volt into mega electron volt, we know that mega means million, that is 10 raised to 6. So 10 raised to 6 electron volt we can call as mega electron volt. So let us simply multiply this with 10 raised to 6. Okay, so when 10 raised to 6 electron volt we can use mega electron volt. But when we multiply with 10 raised to 6, in order to compensate for that, you have to multiply with another 10 raised to minus 6. Otherwise our numerical value will be wrong. So you have to multiply with 10 raised to 6 and 10 raised to minus 6. 10 raised to 6 electron volt I am calling mega electron volt. 10 raised to minus 6 nanometer. What is that? 10 raised to minus 6 nanometer means 10 raised to minus 6 into 10 raised to minus 9 meter, which is 10 raised to minus 15 meter. Okay, 10 raised to minus 15 meter is a small unit of energy which we call femtometer, or sometimes Fermi, named after Enrico Fermi, right? So look at this, the numerical factor here 1240, okay, 1240, it remains the same, or 1240, it remains the same. We have just rearranged the units here. Instead of electron volt, we multiply with 10 raised to 6 and call it mega electron volt. This along with nanometer we multiply with 10 raised to minus 6, and 10 raised to minus 6 into 10 raised to minus 9 we combine as femtometer. So HC we can express in two units. Two units, I mean that means two multiples of electron volt, let us say. Either you can call it 1000, you can use 1240 electron volt nanometer in atomic physics calculations, or 1240 mega electron volt femtometer in both nuclear physics and particle physics calculations. Okay, I have spent some time on this factor. It will be useful in your calculations later. So do this calculation, check the value of Hc and convince yourself. Okay, only then you will remember it. Only when you do it on with your own hands, you will remember numerical factors. Okay, so do this calculation. Now let us look at the photon energy at different regions. I have considered 3 regions. These are important. Okay, that's why I have considered only 3 regions. Visible light. Okay, let us consider red. Red photon has a typical wavelength of 700 nanometer. This we have seen in our previous slide. So what is the energy of this photon? Hc by lambda. We know the value of Hc, 1240 electron volt nanometer divided by 700 nanometer. Okay, your value will be 1.77 electron volt. You can do this calculation and check it. Let us consider the other end, violet, 400 nanometer wavelength. The value of energy will be, if you substitute 400 nanometer here, 3.1 electron volt. Okay, now you can see how convenient it is. If you get the wavelength in nanometer, you don't even have to convert into meter, because numerator already you have a nanometer. This nanometer and nanometer will cancel. You will get the answer directly in electron volt here also. So now you see visible range is this 700 nanometer to 400 nanometer, red to violet. What is the energy? You can see the one with the maximum wavelength will be having lowest energy. Okay, because wavelength is in the denominator in the expression for energy. So the red photon has the minimum energy 1.77 electron volt. Violet photon has maximum energy 3.1 electron volt. So this is the range of the energy of visible photon, 1.77 electron volt to 3.1 electron volt, roughly 2 to 3 electron volt. What about green light, which is wavelength is 500 nanometer, energy is 2.48 electron volt, roughly 2.5 electron volt. Okay, which is in the average of these two approximately. So this I have told you that in atomic transitions between valence electrons, a few electron volt energy is emitted and absorbed. So most of the time the radiation that is emitted and absorbed in atomic transitions, valence shell transitions, is visible light. Okay, UV light also. Okay, but with UV and visible light we can say. A few electron volts are the energy of visible region. For UV region you can do the calculation. Now consider X-ray. Typical wavelength is 1 angstrom. We have seen that. Now if you substitute this, here we have to be careful when you substitute in the lambda in the denominator, because Hc you have expressed in electron volt nanometer, denominator you have to convert into nanometer. Only then these two nanometers will cancel. So 1 angstrom is 10 raised to minus 1. 1 angstrom is 10 raised to minus 10 meter, which you can write as 10 raised to minus 1 into 10 raised to minus 9 meter. That is 10 raised to minus 1 nanometer. Okay. So this 10 raised to 1 will go to the nanometer, will cancel. 10 raised to minus 1 will go to the numerator, which is 10. So you can write this as 12.4 kilo electron volt. So keep in mind that we know the typical wavelength in X-ray region is 1 angstrom. So the typical energy of X-ray photon is a few kilo electron volt. Okay, or 10 kilo electron volt we can say. So or a few kilo electron volt up to some 50, 100 kilo electron volt. So a few kilo electron volt is the rough 10 kilo electron volt, order of 10 kilo electron volt. That's what we can keep in mind. What about gamma ray? Wavelength is typical wavelength is 1 picometer. Substitute that, but here also convert picometer to nanometer. Picometer is 10 raised to minus 12 meter, which is 10 raised to minus 3 times 10 raised to minus 9. That is 10 raised to minus 3 nanometer. Nanometer will cancel. This 10 raised to minus 3 will go to the numerator as 10 raised to 3. Now we have 1240 electron volt into 10 raised to 3, which we can approximate as 1.24 into 10 raised to 6. That is 1.24. 10 raised to 6 electron volt is mega electron volt. So the energy of gamma ray photon is 1.24 mega electron volt. That is, the typical energy of gamma ray photon is or of the order of mega electron volt. Typical wavelength is of the order of 1 picometer, so typical energy is of the order of mega electron volt. Keep that in mind. So we have considered three regions of the electromagnetic spectrum to calculate the photon energy. Visible region has a photon energy between 2 to 3 electron volt. X-ray a few kilo electron volt, okay, or 10 of the order of 10 kilo electron volt. Gamma ray of the order of mega electron volt. In this same way, you can do calculations for the other regions also, that I am leaving to you. Okay. Now we have familiarized ourselves with electromagnetic spectrum. Let us come to our topic, blackbody radiations. First of all, what is a blackbody? This concept was introduced by Kirchhoff in 1860, around the middle of 19th century. So what is a blackbody? Blackbody, you can see here, blackbody is an idealization of any condensed matter at any temperature. What is a condensed matter? It can be solid, liquid and high density gas. Condensed, okay, high density matter. It can be solid, it can be liquid, it can be high density gas. So consider a condensed matter at any temperature. Blackbody is its ideal case. Why we call it an ideal case? Because when we try to heat a body, heat a condensed matter, consider a solid body, we try to heat it. Now heating means we are providing, we are giving heat radiations by way of infrared radiations. When these radiations are incident on a hot body, some of the radiations will be absorbed, some of the radiations will be reflected. Okay. Now what Kirchhoff did was he considered an idealization of this concept of this body. That is, consider a body, solid, liquid or high density gas, which absorbs all the radiations incident on it without any reflection. That he called a blackbody. Okay. So it also emits radiations of all frequencies, because at any temperature it will be emitting radiations also, and we will see that it emits radiations of all frequencies. So this type of a body, an ideal body that absorbs all the radiations incident on it without reflecting any energy, it's called a blackbody. It also emits radiations of all frequencies. So he introduced this concept. Then Kirchhoff postulated that the energy density of radiations emitted by a blackbody, radiations emitted by a blackbody we can call blackbody radiations. Okay, so you consider a blackbody which is in thermal equilibrium. What is meant by thermal equilibrium? Temperature remains constant. How does the temperature remain constant? Because the rate of energy, when the rate of energy absorption and rate of energy emission of a blackbody is the same. Suppose it absorbs 10 joule per second. It also emits 10 joule per second. Then what is the temperature of the body? It remains constant, neither increases nor decreases. If the rate of absorption is greater, temperature increases. If the rate of emission is greater, temperature decreases. If the two rates are balanced, temperature remains uniform. That is a blackbody in thermal equilibrium. So consider a blackbody in thermal equilibrium. Then, okay, we know it absorbs radiations, it also emits radiations. Radiations emitted by a blackbody are called blackbody radiations. Now, if we measure the energy density of these radiations, energy density means energy per unit volume. Okay, let us use the symbol capital U for that. Kirchhoff found that this energy density will be independent of the size of the body, shape of the body, volume of the body and the material of the body. Okay, it will be independent of these factors: size, shape, volume and material of the body. Then what are the factors on which this energy density depends? It's a universal function of the absolute temperature of the body, capital T, and the frequency nu of the emitted radiation. So this energy density of blackbody radiations depend on only two factors. One is the uniform temperature of the blackbody. We know that it is in thermal equilibrium, so its temperature remains constant. So this the energy density depends on that temperature. Secondly, this energy density depends on the frequency of the emitted radiation. So we can write an equation like this: energy density U is a function of frequency and temperature. Why is it called a universal function? Because it is the same function for all black bodies in the universe. Okay, it is independent of size, shape, volume and material of the body. So then it must be same for I am not saying that it is the same, it has the same value, but its functional form is the same for all black bodies in the universe. It depends only on temperature and mu. So as temperature and frequency changes, its value will change. But the way the energy density depends on frequency and temperature, it will be the same for all bodies in the universe, all black bodies in the universe. That is why it is called a universal function, in the sense that it is applicable to all black bodies. Okay, so Kirchhoff essentially postulated the existence of such a function, a universal function of energy density, which depends on two variables: frequency of the black body radiations and temperature of the black body. Now the question is, what is the form of this universal function? These are two aspects. Kirchhoff postulated the existence of such a universal function. Now the second question is, what is the form? What is the functional form of this function? What do I mean by that? This when we say that energy density depends on two factors, frequency and temperature, that dependence, the relationship between frequency and temperature, or the way energy density depends on frequency and temperature, can be anything. It can be many ways. Energy density can be nu plus T, nu by T, okay, e raised to nu by T, e raised to nu into T, sin nu T, we don't know. What is the functional form in which energy density depends on nu and T? Now this was an open question at that time in 1860, and this question is called Blackbody radiation problem. This problem was raised by or defined by Kirchhoff. He postulated, he introduced the concept of black body, he postulated the existence of such a universal function, and this question remained open at that time. What is the functional form of this universal function, or how can we derive this energy density as a function of frequency and temperature, starting from basic principles, starting from first principles. This is called Blackbody radiation problem, proposed in 1860. Consider Blackbody spectrum. The first scientists who worked in Blackbody radiation, so on this problem, were experimental physicists in Germany. Okay, I have written some of their names here. Around 1898, these two persons, Ernst Pringsheim and Otto Lumer, invented an approximate model for a black body. This is such a model. Consider a hollow metallic cavity. Inside is hollow, with a small hole on the surface. Okay. Now, if you send electromagnetic radiations through this small hole, consider one ray. It comes and incident on the inner wall. When it is incident here, some of the radiations will be absorbed, some of the radiations will be reflected. So it is reflected. Again, part of it is absorbed, part is reflected. In this way, this radiation undergoes multiple reflections inside this cavity. During each reflection, one part is absorbed, one part is reflected. So after many such scattering or multiple reflections inside the cavity, it is completely absorbed. So this hollow cavity acts like an approximate black body, right? In order, we can enhance this absorption by blackening the inner walls, making it rough. Okay, and even some projection can be in some figures. You can see a projection here. Okay, which ensures that this radiation will not be backscattered. Okay, if there is a projection here, radiation will be inclined on one side and it will be scattered in some other direction. So this type of modifications you can do. Okay, this type of a hollow cavity was invented by these experimentalists, and you can also as the radiation is absorbed inside the cavity, its temperature increases and radiations will be emitted from the cavity. So radiations coming out through these small holes in the cavity, these are blackbody radiations. We can also call them cavity radiations. Okay, so by the end of 19th century, this type of hollow metallic cavity was used in the experimental study of blackbody spectrum, and regarding the radiations emitted by such a blackbody, their energy density or intensity was measured. This is a typical plot of intensity versus frequency. Okay, we will look more closely at the values plotted along the x-axis and y-axis in the next slide. For the time being, let us look at this diagram. It's a shape. Okay, different graphs corresponds to different temperatures of the blackbody. Look at this inset. This blue graph corresponds to blackbody radiation for a blackbody which is in thermal equilibrium at 3000 Kelvin. This green graph corresponds to blackbody at 4000 Kelvin. Red one 5000, 6000, like that. So for each temperature, the shape is the same, right? So you look at the shape, it increases, reaches some maximum, then decreases. You can also see that it's not exactly a bell-shaped curve. It's not symmetric about the peak. Okay, the higher frequency side is greater. I mean, the area under the, if you draw a vertical line corresponding to the peak here, consider this violet graph, then the area to the right of the peak, high frequency side, is greater than the area to the left of the peak. It's not symmetric about the peak. Okay, this type of a graph is called blackbody radiation spectrum, or simply blackbody spectrum. And this graph, the complete shape of this graph was obtained by the end of 1900, because there were difficulties in making measurements at very low frequencies. Okay, and also at very high frequencies. So intermediate frequency range was first measured, then very high frequencies were measured, also very low frequencies were also measured. So it was towards the end of 19th century, towards the end of 20th century, that means towards the end of 19th century, that is by the end of 1900, that this part, that is this very low frequency part, measurements were completed and this complete shape was obtained. And again, some of the experimentalists who worked during this period in this problem were Henrik Rubens, Ferdinand Kerlbaum. All of them were German experimental physicists. Okay, let us look more closely at this blackbody radiation spectrum. On the x-axis, look at here, frequency of the emitted radiation is plotted in terahertz. Tera means 10 raised to 12. So x-axis we plot frequency. Also wavelength can also be plotted along the x-axis. Okay, we will see what is the difference in the graph when wavelength is plotted. Later we will look at that. Along the y-axis, either spectral energy density or spectral intensity of the emitted radiation is plotted. Here we see the term intensity. When we say intensity, what we mean is spectral intensity. What is this? What is spectral energy density? Let us use the symbol small letter u for that. It is the energy of radiation per unit volume per unit frequency. This word spectral means per unit frequency. So energy per unit volume per unit frequency, that is spectral energy density. Unit will be joule per meter cube per hertz rate per hertz, that is joule meter raised to -3, hertz raised to -1. Spectral intensity means energy of radiation per unit time per unit area per unit frequency. Again, the word spectral means per unit frequency. So intensity is energy per unit time per unit area. Okay, now what is the unit here? Energy per unit time is joule per second, which we call watt. Okay, so watt per meter square per hertz. That is watt meter raised to -2 hertz raised to -1. That is the unit of spectral intensity. Now for electromagnetic radiation, spectral intensity and energy density, I use small letter j for spectral intensity. This spectral intensity and spectral energy density are related by this equation, j equal to c by 4 into u, where c is speed of light in vacuum. You can check this formula whether it is dimensionally correct or not. That is that you can do as a homework. That is take the energy density, okay, spectral energy density, which is this energy per unit volume per unit frequency, and spectral intensity is energy per unit area per unit time per unit frequency. Per unit frequency is the same on both sides. So we want to see when you multiply energy density with the speed, you will get intensity or not. Dimensionally, you can check whether they are same or not. Often this energy density U or spectral energy density U or spectral intensity J is expressed per unit solid angle also. The unit of solid angle is steradian, symbol is SR. Okay, so if you also measure this quantity per unit solid angle, one extra per steradian or steradian raised to -1 appears in the unit. So look at this here. When we say intensity, we mean spectral intensity. Look at the unit watt meter raised to -2, steradian raised to -1, hertz raised to -1. It means the presence of steradian raised to -1 shows that we are also measuring per unit solid angle, and presence of hertz raised to -1 shows that this is not simply intensity but spectral intensity. Okay, so what we have to remember is that whether we plot intensity, that means spectral intensity or spectral energy density along the y-axis, the shape of the graph will be the same, because the difference between the two is only speed of light in vacuum, a constant. So whether we plot u or j along the y-axis, the shape, the overall shape of the graph remains the same. So in the plot of Blackbody spectrum, x-axis we can plot frequency or wavelength, y-axis we can plot spectral density, spectral energy density or spectral intensity. Okay. What are the important features of Blackbody spectrum? There are 4 features. First one is it is continuous spectrum. What do we mean by that? You can see, take any curve, it's a continuous curve. What does it mean? It means that radiations of all the frequencies are emitted. All the frequencies between 0 and a large value. Okay, it may not go practically up to infinity, but a large value. So between 0 and a very large value, all possible frequencies are emitted. So corresponding to all possible frequencies, we get different values for energy density or intensity. It's a continuous graph. You compare this with the case of atomic line spectra. For example, sodium spectrum or mercury vapor spectrum or hydrogen spectrum. We have discussed this in the introductory class. We have seen one of the unsolved problems of 19th century physics was the problem of atomic line spectrum. Why they are unique. Okay, why they are line spectrum, why they are unique, and why there is a correspondence between emission line spectrum and absorption line spectrum of the same element. You consider, for example, emission line spectrum. On a dark background, you have bright lines at specific wavelengths. So there are emissions only corresponding to different discrete wavelengths. Here it is not like that. All wavelengths or all frequencies are emitted. That is the meaning of continuous spectrum. Second point is intensity is small at very low and very high frequencies. See, at very low frequencies, the graph is here, intensity is small. At very high frequencies also, the intensity is small. In between, it reaches a maximum and then decreases. So at very low frequencies and very high frequencies, intensity is small. That's the second feature. Third feature, as temperature increases, the area under the curve increases. Obviously, you can see we have 6 curves here for different temperatures. So as the temperature increases from 3000 Kelvin to 8000 Kelvin, you can see that the area under the curve increases. What does it mean? What is the meaning of area under a curve? If you plot a function f of x along the y-axis and the independent variable x along the x-axis. What is you get some curve. What is the meaning of area under the curve? It is integral f of x dx. Area under a curve is given by integration of that function. Okay, so area under this curve is integral of intensity with respect to frequency. What do we get when we integrate intensity with respect to frequency? Intensity is actually spectral intensity, right? So the small letter j indicates energy per unit time per unit area per unit frequency range. Okay, so if you multiply j with some small frequency range d nu, what we get is energy per unit area per unit time in that frequency range d nu. When you integrate it from the minimum frequency 0 to a maximum frequency infinity, what you get is integral 0 to infinity j d nu. That is total energy density, total intensity, if you are using j, total intensity emitted from having from frequencies from 0 to infinity. So the area under the curve is integral j d nu, which is the total intensity of the emitted radiations. Okay, so as the temperature increases, the area under the curve increases. It means the total intensity of emitted radiations increases with temperature. Okay, now the fourth feature is that as the temperature increases, the peak of the curve is shifted to the right. See, blue, green, red, yellow, light blue, violet and yellow. You can see that as temperature increases from here to here, the peak of the curve is shifted to the right. To the right means on the x-axis we are plotting frequency. So to the right means to the high frequency side. So we can say the fourth feature is that as temperature increases, the frequency corresponding to maximum intensity. Peak means that intensity is maximum. So the frequency corresponding to maximum intensity increases with temperature. These are the four important features of Blackbody spectrum. It's a continuous spectrum, that is radiations of all frequencies are emitted. Then intensity is very small at very low frequencies and very high frequencies. As temperature increases, the area under the curve increases. That means the total intensity increases with temperature, total intensity of the emitted radiations. As temperature increases, the frequency corresponding to peak intensity, maximum intensity increases. Okay. The third feature that we have seen in the previous slide, this was explained by these two physicists, Joseph Stefan and Ludwig Boltzmann. This is called Stefan-Boltzmann Law. Their law states that the total intensity of the emitted radiations is proportional to the fourth power of the absolute temperature of the black body. That is, this capital J is proportional to T raised to 4. We have seen that, look at the curves here, as temperature increases, the area under the curve increases. That means the total intensity increases. That increase is quantitatively explained by these two. That is, J is proportional to T raised to 4. That means, for example, if temperature is doubled, energy intensity becomes 2 raised to 4. That is 16 times. Okay, this is why there is a rapid growth in the area when the temperature increases. Okay, for example, this dark blue has temperature 3000 Kelvin. This light, I think light blue. Yeah, fourth one, light blue has 6000 Kelvin, this one. So from dark blue to light blue, temperature is doubled from 3000 to 6000. Area becomes very large. Actually, area becomes 16 times larger, 2 raised to 4. Okay, so the rapid growth in the intensity or area is explained because by this relationship. Okay, J is proportional to T raised to 4, and this proportionality constant is called Stefan's constant. Its value is 5.67 into 10 raised to minus 8, and the unit will be J by T raised to 4. Okay, J in intensity has, total intensity has the unit watt per meter square. Then there will be T raised to 4 in the denominator, so per Kelvin raised to 4. So the unit is watt meter raised to minus 2 Kelvin raised to minus 4. This is Stefan-Boltzmann law. The fourth feature was explained by Wilhelm Wien, called Wien's displacement law. This is the law. The wavelength corresponding to maximum intensity, let us say lambda maximum, is inversely proportional to the absolute temperature of the black body. That is, lambda maximum is inversely proportional to 1 by T, or equal to some constant by T. Earlier we have seen the fourth feature was that as temperature increases, the frequency corresponding to maximum intensity increases. It is shifted to the right. That means increases. So if frequency corresponding to maximum intensity increases, wavelength corresponding to maximum intensity decreases. That decrease in wavelength with respect to temperature is exactly a linear relation. That is, lambda maximum is inversely linearly decreases with temperature. That is inversely proportional to temperature. That is Wien's displacement law. So this explains the shift in the peak of the curve as temperature increases, and this constant in the Wien's displacement law, its value is 2.898 into 10 raised to minus 3. Unit will be lambda maximum into T. Lambda is wavelength, that is meter as a unit. T is temperature, so Kelvin, so its unit is meter Kelvin. This is Wien's displacement law. Let us spend some more time on Wien's displacement law. When frequency is plotted along the x-axis, the shift is towards right. That we have already seen. That means nu maximum. Okay, this is the this is not maximum frequency. This is the frequency corresponding to maximum intensity. The frequency corresponding to the peak of the curve. Nu maximum increases with temperature. That is why the shift is towards right. But when wavelength is plotted along the x-axis, here along the x-axis wavelength is plotted. Along the y-axis, instead of intensity, spectral energy density is plotted. So I have told you that whether we plot spectral intensity or spectral energy density, shape will be the same. But the subtle difference here is that we are plotting wavelength along the x-axis. Then as temperature increases from 3500 Kelvin to 5500 Kelvin, as temperature increases, the peak wavelength, the wavelength corresponding to maximum intensity, is shifted to the left side. Here the shift is to the left side. That is, wavelength decreases. Naturally, when peak frequency increases, peak wavelength should decrease. So when you are plotting wavelength along the x-axis, the important difference in behavior is that the shift is shift in Wien's displacement law is towards left. Let us see Wien's displacement law in action on a familiar setup. We are consider heating of an iron rod. Okay, so the maximum temperature is in the middle of this oven. So iron rod is showing different colors at different regions. Here it is red. Okay, away from the oven it is showing dull red color, then bright red color, then orange, then yellow. In the middle of the oven it is almost white. Okay, so here the temperature, as temperature varies, dull red color is having minimum temperature, then bright red color is having higher temperature, orange is having still higher temperature, yellow is having still higher temperature. White means at this very high temperature, all the wavelengths are emitted, all the wavelengths in the visible region. So what we are observing here is a cumulative, a composite light. That's why it is white. So let us so we have seen the difference in colors. Now let us look at their wavelengths. When we move from dull red to bright red to orange to yellow and towards white, the wavelength steadily decreases. So this is Wien's displacement. As temperature increases, the peak wavelength, the intensity of the wavelength corresponding to maximum intensity decreases. Okay, so as temperature increases, as red to orange to yellow to white. Okay. Consider an important application of Wien's displacement law. So it is a relationship between lambda maximum and temperature of a black body. Okay, lambda maximum is equal to some V by T. If we know the wavelength corresponding to peak intensity emitted by a black body, we can calculate its temperature. Okay, so the application is this: if we can measure the peak wavelength in the spectrum of a star, then we can calculate the surface temperature of the star using this law. You can see an example here in this table, in the fourth row. Okay, sun. In the case of sun, if you look at the sunlight, yeah, sunlight contains many frequencies, right? From very low frequencies to very high frequencies, sun is emitting. Now, sun is like a high density plasma. Okay, so it is like high density gas. It's not in the gaseous state, it's in the plasma state. So this high density plasma, which is essentially a gas of charged nuclei, charged particles and free electrons. Okay, positively charged nuclei and free electrons. That such a collection in high density is called a plasma. Now it is high density plasma, so it is like a condensed matter. It is like an approximate black body. So when we measure the intensity of various frequencies emitted by the sun, okay, there are radio waves, microwaves, visible region, ultraviolet, X-ray, gamma ray, etc. are emitted from the sun. The curve that we obtain when we plot this type of a curve, the curve we obtain in the case of sunlight will be approximately like a black body. What about the peak? The peak wavelength is, or the peak region is visible region. So in the sunlight, the maximum intensity region is visible region. It's not accidental that the living organisms on the earth, the eyes of the living organisms on the earth, including ourselves, are sensitive to the visible region of the electromagnetic spectrum. Okay, in the entire electromagnetic spectrum, our eyes are sensitive to this particular band from 700 nanometer to 400 nanometer. The reason, why is it so? Why is that our eyes are not sensitive to X-ray, for example? The reason is that when life was evolving, life has been evolving on the surface of the earth, the most dominant source of light in our environment is sun, right? And what is the peak intensity of the sunlight? It's in the visible region. Okay, then naturally during evolution, all the living organisms on the earth evolves or their eyes are evolved in such a way that the eyes are sensitive to the nearest light source. Suppose our nearest light source, the star like sun, the sun was emitting light whose peak wavelength corresponds to X-ray region. Then our eyes might have been sensitive to X-ray region. Our visible region must have been X-ray region. Okay, so there is the direct connection between our visible region and the peak wavelength of the sun. And the peak wavelength of the sun is around green. In the yellow-green region, it's nearly 500 nanometer. Okay, so lambda maximum is 500 nanometer for the sun. Then you can substitute in Wien's displacement law and you can calculate lambda maximum equal to B by T. Using that equation, we can calculate the surface temperature of the sun. It is around 5800 Kelvin. You check that calculation. Okay. Similarly, other solid bodies that are familiar to us, we can treat them as approximate black bodies. Consider a tungsten filament. Okay, a tungsten filament, if you know the temperature, you can calculate lambda maximum. If you know lambda maximum, you can calculate the temperature. Tungsten filament, when you use nowadays, tungsten filaments are very rare. Okay, they are replaced by CFL lamps or other lights, right? LED lights. So in a typical tungsten filament, the temperature is nearly 2000 Kelvin. And the peak wavelength is 1.5 micrometer, which is in the infrared region. In other words, a tungsten filament emits more heat than light. Light will be there, but heat also will be there. So that is why tungsten filaments are not good, in the sense that a large part of the electrical energy will be lost as heat energy. Okay, so it's not a very efficient, energetically efficient and economically also. Then consider Earth. Assume that Earth is emitting like an approximate black body. Earth, when you observe, when you measure the radiations emitted by the Earth, then the peak wavelength is in the infrared region, 10 micrometer. We know that micrometer is in the infrared region. So this is in the infrared region. Earth is like a giant hot body emitting in the infrared region. The corresponding lambda maximum So this is lambda maximum. The corresponding temperature when we calculate from Wien's displacement law, it is around 287 Kelvin, or if you convert into Celsius, 14 degrees Celsius. Okay, that is the average temperature of the Earth. It's very low temperature. Again, you do this calculation, you check these values once more. Consider human body. We know that the surface average body temperature is 37 degree, which is 310 Kelvin. Then if you assume that our body is emitting like a black body, approximate black body, then the peak wavelength is again in the infrared region, approximately 9.35 micrometer in the infrared region. Okay. So you can check these values. Once you know temperature, you can calculate lambda maximum. In the case of starlight, you can measure lambda maximum using spectroscopic techniques. From that, you can calculate the surface temperature of the star, as in the case of sun I have shown here. So that is one of the main, the important applications of Wien's displacement law. By measuring the peak intensity or peak wavelength from starlight or stellar spectra, we can calculate using Wien's displacement law the surface temperature of the star.